guys, welcome to this video. We're going to have a look at the idea of using the definite integral to help us calculate some areas that are underneath a curve but bounded by a few boundary lines, a couple of vertical lines and the x-axis, okay, sort of like shown in this diagram down here, or even this one here. Okay, just referring you to the OneNote here. Okay, there are a few notes about this, and what I'd ask you to do is to actually have a look at this video here, where a quite reasonable proof, okay, of the basic result of how to use a definite integral to calculate the area under a curve is given. Now in this video I'm going to assume that the result of using the definite integral to help us calculate area is true, and then have a look at a few examples. Okay, so let's jump over to that now. Okay, so here I've got a bit of a diagram drawn up, okay, where we've got the usual x and y axes, a curve given by some sort of function of x, and a red line representing part of that function, and we're interested in the area underneath that curve, but between a couple of boundary lines given by x equals a and x equals b, which would produce these vertical dashed lines here. And so we're interested in this area here between the curve, the boundaries a and b, and the x-axis. So I'm just trying to roughly shade that in. Okay, so that's rough representation of that area. Now the result that I'm using is that this area is given by a definite integral, and it's between the limits of a and b, so it's a definite integral again of that function. Now we'll see some situations where the area might be underneath the x-axis, where we've got to use the definite integral, but in a slightly different way to help us with that situation. Also, sometimes we might be interested in the area between two curves, so we might have to calculate a couple of areas and say subtract the two areas from one another, or look for a shortcut in that situation. But anyway, let's press ahead and look at a specific example. Okay, so what I'm going to do here is I'm going to take a pretty typical function of x. Okay, so let's draw one up here. So just get a bit of an axis going here. Oh, that didn't work so well, did it? Where'd my line tool go? That wasn't it. Okay, so let's try that again. Okay, and let's draw a rough representation of the function y equals x squared. Okay, so that would, just roughly drawing that in here, it's meant to be symmetrical, and that roughly is, okay, not perfect, but it will do. So I'm just going to draw more firmly in that right hand part, and let's say we're interested in the area underneath the curve between x equals 2 and let's say that this was x equals 5. So we're interested in this area, and I'll just shade it in a slightly different color. Okay, so this yellow area here. Okay, so according to this result here, Well, this area, and let's just call it A for area, should be equal to the integral, the definite integral between 2 and 5 of that function x squared. Okay, and if we accept that that is true, using this result here, which by the way is called the fundamental theorem of calculus, okay, is then going to simply be the result of when I calculate that definite integral. So integrating would give me x cubed over 3, and then because it's a definite integral I need to calculate that. So it'd be 5 to the power of 3 over 3, take away 2 to the power of 3 over 3, and I just realized I don't have my calculator here, so I'm just going to pause the video here for a sec. Okay, so I'll grab my calculator, plug that in, and I've got a result of 44 1/3. Now, you may be wondering, hold on, this is an area, so shouldn't there be units? And you'd be absolutely right if you were thinking that. Now, because we don't know what the units are, we're simply going to put units, and because it's area, units squared. Okay, so that's a pretty straightforward example of using area underneath a curve and calculating it. Okay, so let's have a look at a slightly more complicated one. Now, once again, I'm just going to pause the video here so I can draw up a bit of a diagram and set the integral up, and rather than you watching me draw all that up, I'll just pause that for now. Hi guys, welcome back. Just pause the video just so I could draw up this pretty rough but I think reasonable looking curve here. So what we are going to try and do is to have a look at the situation where we've got an area that we're after which is underneath the x-axis here, so this area here. Now what you might notice, I haven't put the function here yet, and I'm hoping that you might be able to tell me what that function is. Well, if you look carefully there, it's a sine curve and the amplitude is 5. And one other thing I'd ask you to notice, what's the period of the graph? Okay, how long does it take before it repeats itself? From 0 to pi. So what would be the equation of that? Well, hopefully you can remember some of your trig work. It should be 5 sine, and what's going to go in here? Yeah, it'll be 2x. Okay, so we're going to try and integrate then to get the area shown in yellow here. Now what I'm going to do is I'm going to calculate this definite integral between the limits of pi and pi over 2, and I'm deliberately not saying that's equal to the area at the moment because you'll see that there is going to be a bit of a complicating factor here. Anyway, let's calculate this definite integral. So what's the integral of a sine function? What's that again? I think it's negative cosine. Okay, and so bearing in mind that we've got a 5 in front, so it should be minus 5. Then we've got to bring into account the fact that we've got that 2 there, so I reckon our constant in front, let's get rid of that, should be negative 5 over 2 cosine 2x. Now let's just check that for a moment before we continue. Now if I derive this, so let's just pull that check over here. Okay, so if I derive at negative 5 over 2, the derivative of cosine is negative sine of 2x times 2 because of the chain rule. So that will cancel with that. The negatives will cancel, and I've got 5 sine 2x, which is what I started with. So that's all good. Okay, it looks like we've got the correct integral here. Okay, so having done that, let's now plug in our limits. So cosine of 2 times pi, well, that will be 2 pi. and we're going to subtract from that what we get when we put pi over 2 in. So it'll be the cosine of 2 times pi over 2, that'll be pi, and let's see what we get. Okay, well, we should be able to calculate some of these things manually. Okay, bearing in mind, very quick, well, that's a terrible axis. Let me get rid of that and try that again. Maybe just actually go with the line tool here for a second. Just trying to draw a quick sketch of cosine. Okay, now cosine looks roughly like that, and this was pi, and that was 2 pi. Okay, so what do we got? Cosine of 2 pi is equal to 1. So that's going to be negative 5 over 2 times 1, negative 5 over 2. Cosine of pi was negative 1. So that's going to be minus negative 5 over 2 times negative 1. Hopefully you don't get 0 here. Okay, so that's going to be positive pi over 2, so it becomes minus positive 5 over 2, so that's equal to negative 2.5 minus another 2.5, so minus 5. Okay, so what does that mean? Well, our definite integral has given a negative result. Now, the concept of area means how much room does a flat surface take up? Well, it can't be negative. Can't draw me a negative area. But the definite integral has come out to be negative. And the reason, the question is, well, why is that happening? It turns out that when you've got an area which is underneath the x-axis, and you calculate the definite integral like this, that it comes out to a negative. So what we need to say is that the area then would equal the absolute value of this. This area here would be exactly the same size as this one here, and that is positive 5 if we calculated it. So this area here is still 5, but the definite integral being negative 5 has to be adjusted to give us the correct area. So I can therefore say, well, therefore the area is equal to the absolute value of that, which is 5 units squared. Now, if you want to put definite integral symbols around this and put a equals in front, you can do that, but then you've got to carry them all the way down. Okay, and that to me is just unnecessary writing. We can simply cover that by saying, well, the area is equal to this here then, just with one statement at the end. So the key thing is to realize that, okay, the definite integral where the area is underneath the x-axis is going to be negative. Definite integral, get that eraser working, is negative in that situation. Therefore the area would equal the absolute value of that definite integral result. Okay, so you may be wondering, well, what do you do if you've got part of the area above and part below? Let's have a look at that in another example just in a moment. So I'm just going to pause the video and draw one of those up. Okay guys, got a bit of an example drawn up here. I'm actually taking one from your workbook just for a moment. Okay, and this is number 173 on page 205. So what we've got here is a pretty typical cubic graph shape, and here is its equation given in two forms. Okay, so here we've got the cubic as a polynomial, and then the same polynomial but in factorized form. So what we want to do then is to get the area shaded. Now what you should notice is that part of the area is above the x-axis and part below. And what they haven't done for us is to put any sort of values on the x-axis here, hoping that we can figure those out for ourselves. And yeah, we're up for that, aren't we? So using this factorized form here, we should be able to put these numbers in that are going to be the x-intercepts, which will be when y equals 0, which will be when each of these factors is 0. So 0 in the middle there, okay, looks like a -1 here, that's that one, 0 there, and that is going to be a 2. Okay, so what do we do about trying to get the area? Well, just want to make a note of this. Okay, this is the wrong way to do this question. Now, why would I point out the wrong way? Because quite often, typically, I see students do something like this and they go, oh, okay, I'm just going to integrate between -1 and 2, and then they integrate this function, and then they do a whole lot of great work and they get some sort of result, okay, which is totally wrong. The problem with that, remember the previous example, is that the definite integral between 0 and 2 is negative, but the definite integral between -1 and 0 is positive. So what this definite integral would effectively calculate is the difference between these two areas. It's like taking that area there, that positive definite integral, and subtracting that negative definite integral, resulting in, well, even if you get a negative answer and you take the absolute value of it, there's still a difference between those two areas. So that would be incorrect. So what do we do? Well, we need to split the area up into two parts. Okay, so I'm going to calculate two definite integrals. I'm not going to call any of them the area yet. I'm going to calculate this definite integral. Okay, then I'm going to calculate another definite integral, and I'll put the working for that down here. Between 0 and 2, same function. And any definite integral that comes out with a negative value, I'm going to take the absolute value of it and then add it to the other definite integral, the positive one, to get the overall area. So let's just get into the working here. So integrating, that was an x squared, that was terribly written, wasn't it? So minus x cubed over 3, and it'll be minus 2x squared over 2. The x squared would cancel. Okay, so, sorry, the x squared would cancel, the 2 would cancel, just leaving x squared. 0, -1. Okay, now putting 0 here, here, and here is going to give 0, minus what we get when we put -1 in. -1 to the power of 4. That's -1. Negative quarter then for that bit. Okay, -1 cubed. What did I just say? -1 to the power of 4 is +1. So that is positive a quarter. -1 to the power of 3. That's definitely -1. So negative a third, but minus negative a third becomes plus 1/3. -1 squared is +1, so minus 1. Okay, so what's this going to give? Okay, so 0 minus, okay, so what's that going to be? Well, I think I'm actually going to do a little bit of fraction work here. Let's put them all over 12. Common denominator. So that's going to be 3/12 plus 4/12 minus 12/12. 0 minus, that's 7, take away 12, that's going to be minus 5. So minus, and there's something screwy going on here, because I did not expect to get a positive result for this area. So I'm just going to pause the video and check my working, because I think I made a mistake here somewhere. Okay, I feel a bit like an idiot. Okay, yes, you probably realise I was calculating this definite integral over here for this positive area, so I think my working's correct, and yes, it is positive 5/12. So that in fact is the area of this portion here. Okay, let's get this definite integral for this part, and this should come out to be negative. Okay, so having done the integration work, unless I've made a mistake there somewhere, I can just go and use that result because I've already done that work. Just want to put different limits in. Okay, so 2 to the power of 4 is 16. 16 divided by 4 is 4. 2 in here, that becomes minus 8/3. 2 in here becomes minus 4. Take away from that what I get when I put 0 in. Now 0 there, there and there, still 0. So the 4's cancel and we end up with negative 8/3. Okay, so what's our overall area equal to? So therefore the area is going to equal the absolute value of that plus our 5/12. Okay, so let's tidy that up. So that's going to be, let's put this over 12. So times 4 times 4, that's going to be 32/12 plus 5/12. That's 37/12. Okay, and 12 goes into 37 3 times. 3 times 12 is 36, 1 left over. So 3 and 1/12 units squared. Okay, so unless I've made an error in my arithmetic somewhere or in my integration, which I don't think I've done, that should be our area then. Okay, I'm going to stick in a couple of questions here similar to these kind of ones. So have a go at those, and we'll see you in class following period. Okay, so good luck with those.